So in this video I'm going to be presenting 4 proofs for the summation formula of the complex roots of unity. So you might observe that this formula doesn't really work for n equals 1. Therefore we're going to presume that n is greater than 1. If you substitute n equals 1, you're going to get in the left side, you're going to get 1, and in the right side there is 0, and consequently you obtain that 1 equals to 0. So for n equals 1, this formula doesn't hold. So the first proof involves the utilization of geometric progressions. Now, this sum, this expression, is actually the sum of consecutive terms of the geometric progression. So you only have to see that the first member of this sum is 1, so a1 is going to be 1, and the ratio, the common ratio of the geometric progression is e to the 2 pi I divided by n. Now, what you end up doing is that you substitute to the formula of the summation of the consecutive terms of the geometric progression. So a1 is going to be 1, q is going to be e to the 2 pi I divided by n, and so on. Now, how you can manipulate this expression is that e to the 2 pi I divided by n to the power of n is going to be 2 pi I n divided by n. So you're simply multiplying the other exponent with this exponent. So n in the numerator is going to cancel out n in the denominator. Therefore, you obtain this formula, e to the 2 pi I minus 1 divided by e to the 2 pi I divided by n minus 1. Now, e to the 2 pi I is simply going to be 1 because you are rotating that vector with 2 pi, and therefore it's going to just arrive to the same place where it has been. And what you should now see is 1 minus 1 is going to equal to 0, and if the numerator is 0, then the entire expression is going to be 0, concluding our proof. Now, you have to also see that if we are not explicitly saying that n should be greater than 1, then this denominator is going to be 0 as well, and therefore this argument doesn't really work for n equals 1. Now, the second proof is going to involve the V8 formulas. So now, because we presume that n is greater than 1, we can write this polynomial in this specific way. So it's x to the n plus 0 times x to the first power minus 1. Now, this is exactly the polynomial whose roots are exactly the complex roots of unity. Now, with the utilization of V8 formulas, you observe that the sum of zeros of fx is always going to be this. So minus 1 multiplied by the coefficient belonging to x1 divided by the coefficient belonging to x to the n. That's how the V8 formulas are operating. You can prove it for yourself pretty easily. And now, because of that, this sum is going to equal to minus 1 multiplied by 0 over 1. And because this numerator is 0, this entire fraction is going to be 0 too, and consequently this whole term is going to end up being 0, concluding our proof. Now, you should observe too, in this case, that for n equals 1, this proof doesn't really operate, because then the coefficient of x to the 1 wouldn't really be 0. Now, a third proof involves rotations. So what it means to multiply by w is that you're multiplying by e to the 2 pi I divided by n, and it's actually a rotation with this angle. So if you're multiplying this entire sum by w, then all of these roots of unity will be shifted to the next one. So all of them is going to be rotated with this angle. Therefore, the entire sum is not being altered. So we are getting the same results. Therefore, it's simply an equation which you should solve for the sum. Now, and because w is not 1, therefore the only solution is that this sum is going to equal to 0, and therefore obtaining the result which we wanted. Now, it's needless to say that if w is 1, then this proof doesn't really work, and w being 1 is equivalent with n being 1 in this context. Therefore, we can see why this argument doesn't work for n equals 1. Our next proof involves the utilization of polygons, of regular polygons. Now, if we are taking these numbers, these 1 e to the 2 pi I divided by n, e to the 4 pi I divided by n, so on and so forth, these are the complex numbers. And when you are talking about the vectors pointing to these complex numbers, then these are exactly the vectors which are pointing to the vertices of this regular polygon. And taking the summation of these means that you are calculating the resultant force of the linear forces which are acting on the polygon under consideration. So now you only have to see that these forces are equal in length, so the vectors corresponding to the forces have equal length, and the angle between the consecutive vectors are the same. And this means that if we are calculating the sum of these vectors, then you're going to end up obtaining the zero vector. And therefore, this concludes our point.